Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Let your shoulders drop, your breathing slow, as we explore something remarkable that's unfolding in the world of technology. Autonomous coding agents are no longer just helping programmers write software. They're taking complete ownership of entire development workflows. What's most surprising is that programmers aren't fighting this change. They're embracing it, even as it fundamentally transforms their profession. Tonight, we'll journey through this transformation together, one gentle step at a time. Let's begin by looking back at how programming itself has evolved, from those earliest days when every instruction had to be crafted by hand. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Now, without further ado, let's fall asleep. Picture yourself standing in a vast automotive factory from the 1920s, where every single bolt, wire, and gear must be placed by hand with meticulous precision. This is what programming felt like in the earliest days of computing, when developers worked directly with machine code, flipping individual switches and feeding punch cards into room-sized machines. Each instruction had to be crafted at the most fundamental level, telling the processor exactly which memory addresses to access, which registers to use, and how to manipulate raw binary data. There was no abstraction, no helpful shortcuts, just the pure, unforgiving language of ones and zeros that the machine could understand. As the field matured, assembly language emerged like a well-organized toolshed where each implement has a clear label and designated place. Instead of working with incomprehensible binary sequences, programmers could now use mnemonics, short abbreviations that represented common operations, making their code somewhat more readable and maintainable. Add, SUB, MEW, and JMP became the vocabulary of a new generation of developers who could think in terms of operations rather than raw bit manipulation. This was still incredibly close to the metal, requiring intimate knowledge of the processor's architecture, but it represented the first crucial step toward making programming accessible to human minds rather than just machine logic. The introduction of high-level programming languages transformed the landscape, like a river carving new channels through previously impassable terrain, creating pathways where none had existed before. Languages like Fortran, COBOL, and later C allowed programmers to express complex algorithms using syntax that resembled mathematical notation and natural language constructs. Instead of managing memory addresses manually, developers could declare variables with meaningful names. Instead of jumping to specific memory locations, they could use loops and conditionals that mapped directly to human problem-solving patterns. This abstraction layer meant that a single line of high-level code could represent dozens or even hundreds of assembly instructions. The evolution continued with object-oriented programming, which introduced concepts that worked like a sophisticated library system, where knowledge is organized into interconnected but distinct collections. Classes became blueprints for creating objects, encapsulating both data and the methods that operate on that data, while inheritance allowed new classes to build upon existing ones, extending and specializing their behavior. This paradigm shift enabled developers to model real-world entities and relationships directly in code, making large software systems more manageable and maintainable. Polymorphism allowed the same interface to work with different underlying implementations, creating flexibility that was previously unimaginable. The rise of interpreted languages and dynamic typing brought a new fluidity to programming, like switching from carving stone sculptures to molding clay that remains pliable throughout the creative process. Languages like Python, JavaScript, and Ruby prioritized developer productivity and expressiveness over raw performance, allowing programmers to iterate quickly, test ideas rapidly, and focus on solving problems rather than managing low-level details. Variables could change types during execution. Functions could be passed around like any other data, and entire programs could be modified while running. This flexibility came with trade-offs in performance and memory usage, but for many applications, the increased development speed and reduced complexity were worth the cost. Modern integrated development environments evolved into something resembling a master chef's kitchen, where every tool is perfectly positioned, ingredients are pre-prepared, and sophisticated equipment automates routine tasks. IDEs began offering intelligent code completion, real-time error detection, automated refactoring, and seamless integration with version control systems, databases, and deployment pipelines. Developers could now focus on the creative and logical aspects of programming, while the environment handled syntax checking, dependency management, and many other mechanical tasks. The feedback loop between writing code and seeing results shortened dramatically, enabling a more iterative and experimental approach to software development. The emergence of frameworks and libraries created an ecosystem that functions like a thriving marketplace, where specialized vendors offer pre-built solutions for common problems. Instead of implementing every feature from scratch, developers could leverage battle-tested components for user interfaces, database interactions, network communication, and countless other functionalities. React revolutionized front-end development. Django and Rails streamlined web application creation, and TensorFlow democratized machine learning implementation. This abundance of reusable components meant that building complex applications became more about assembling and configuring existing pieces rather than crafting everything from raw materials. Version control systems, particularly Git, transformed collaborative development into something resembling a sophisticated document collaboration platform where multiple authors can work simultaneously without chaos. Branching allowed developers to experiment with new features in isolation. Merging enabled the integration of parallel work streams, and the distributed nature meant that every developer had a complete history of the project. Code reviews became standard practice. Continuous integration pipelines automated testing and deployment, and the entire development process became more transparent and accountable. Teams could now work across time zones and continents with unprecedented coordination. The advent of cloud computing and containerization changed deployment and scaling, like transforming a traditional farm into a modern hydroponic facility where resources can be precisely controlled and optimized. Applications could now be packaged with all their dependencies into containers, ensuring consistent behavior across development, testing, and production environments. Auto-scaling meant that resources could expand and contract based on demand, and microservices architecture allowed different parts of an application to be developed, deployed, and scaled independently. Infrastructure became code, managed through version control and automated deployment pipelines. AI-assisted coding tools represent a fundamentally different kind of evolution, operating like having a knowledgeable apprentice who can anticipate your needs and suggest solutions before you fully articulate the problem. Tools like GitHub Copilot, powered by OpenAI's Codex model, and ChatGPT can generate entire functions from natural language descriptions, suggest completions that go far beyond simple syntax, and even help debug complex issues by analyzing code patterns and identifying potential problems. This isn't just automation of routine tasks, it's augmentation of human creativity and problem-solving capabilities, allowing developers to work at a higher level of abstraction and tackle more ambitious projects. The current frontier involves autonomous agents that function like having a skilled contractor who can take a high-level project description and independently handle the planning, implementation, and testing phases. These systems, built on large language models trained with human feedback, can break down complex requirements into manageable tasks, write code across multiple files and modules, run tests to verify their implementations, and even iterate on their solutions based on feedback. Unlike traditional automation tools that follow predetermined scripts, these agents can adapt their approach based on context, learn from mistakes, and make decisions about architecture and implementation strategies, representing a qualitative shift from tools that assist human programmers to systems that can perform substantial portions of the development process autonomously. What makes this evolution particularly significant is the compression of the feedback loop, like replacing a traditional postal system with instantaneous communication that enables entirely new forms of interaction. Where once a developer might spend hours or days implementing a feature, testing it, and refining the implementation, modern AI agents powered by foundation models can potentially complete this cycle in minutes or seconds. This speed enables a more experimental approach to software development, where multiple solutions can be rapidly prototyped and evaluated, and where the cost of trying new ideas becomes negligible, fundamentally changing the bottleneck from implementation time to problem definition and solution evaluation. The implications extend beyond mere productivity improvements to fundamental changes in how we think about software architecture and system design, like moving from constructing buildings with fixed blueprints to growing organic structures that can adapt and evolve in real time. When implementation becomes nearly instantaneous, the traditional trade-offs between flexibility and performance, between generality and optimization, begin to shift dramatically. Systems can be designed to be more modular and adaptable because the cost of refactoring and rebuilding components approaches zero. This could lead to software that evolves continuously rather than being deployed in discrete versions. Looking forward, this progression suggests we're approaching a phase where the primary human role shifts from direct code creation to system orchestration and quality assurance, much like how a conductor guides an orchestra without playing every instrument directly. Developers will increasingly focus on defining requirements, evaluating outcomes, and ensuring that autonomous systems are building software that meets real-world needs and maintains appropriate safety and security standards. The skill set required will emphasize understanding business domains, user needs, and system integration rather than syntax mastery and algorithm implementation. This represents not the end of programming, but its transformation into something more strategic and creative, where human insight guides increasingly capable autonomous systems in creating the software that shapes our digital world. Take a moment to let that sink in. How programming began with such manual, painstaking work, every single instruction crafted at the most basic level. It's quite something to imagine those early programmers working directly with ones and zeros. Breathe gently as you consider how far we've come from those punch card days. Now, let's see how this foundation of human craftsmanship has evolved into something where AI agents are learning to improve themselves through real-world experience. We'll explore how companies like OpenAI have created systems that grow better at their tasks with each passing week. Imagine a garden where each plant learns to grow better by watching how the gardener tends to it, then teaching itself new techniques overnight. That's essentially what happened when OpenAI and Thrive Holdings set out to build Tax AI, a system designed not just to help accountants prepare tax returns, but to continuously improve itself based on real-world feedback. Over 6 months, their collaboration with Kreet's network of 30-plus accounting firms created something remarkable: an AI agent that processes thousands of tax returns while getting measurably better at its job with each passing week. Picture a master craftsman's workshop where every tool becomes more precise through use, each project leaving behind traces that inform the next creation. The challenge they faced was familiar to anyone building production AI systems. Laboratory performance rarely translates directly to real-world deployment. Traditional feedback loops are painfully manual, requiring engineers to hunt down edge cases, adjust prompts, and slowly translate production failures into lasting improvements. But with Codex's frontier capabilities, thoughtful evaluation infrastructure, and direct access to practitioners working in genuine environments, the team envisioned something different: agents that could advance themselves. Consider a busy restaurant kitchen during the dinner rush, where every order represents a complex coordination of ingredients, timing, and presentation. Crete's accounting practitioners face a similar intensity during tax season, preparing tens of thousands of returns that require working through millions of underlying documents. From medium to large complexity filings, data entry alone consumes 8 hours per return, involving messy data sources, prior year documents, and painstaking manual extraction and calculation. The practitioners identified tax preparation as their most significant bottleneck during the busiest stretch of their professional year. Think of a river that starts as a small stream but grows stronger and more capable as tributaries join its flow. Tax AI processed 7,000 tax returns across participating Crete firms during the pilot season, automating much of the time-intensive work involved in preparing 140 and 141 returns. The system saves practitioners about a third of their preparation time, drafts returns with up to 97% accuracy, and increases throughput by roughly 50%. But perhaps most compelling is that the system today is measurably superior to the version deployed just 3 months earlier. Envision a student's gradual mastery of a musical instrument, where progress can be measured by increasingly complex pieces performed with fewer mistakes. The team quantified Tax AI's improvement by tracking how accurately it could complete returns without requiring later correction. They measured accuracy by checking what share of returns reached 75%, 90%, or 100% correct field completion. At launch, only a quarter of returns achieved 75% correct field completion, but within 6 weeks, 86% hit that benchmark. The system showed even faster growth at the 90 and 100% thresholds. Picture a mountain climber who begins with easier trails but gradually tackles more challenging peaks as strength and skill develop. Early on, Tax AI handled simpler work like W-2s and 1099s, but as the season progressed, it moved into more complex returns involving K-1s, schedules, and harder edge cases. Each new capability saved more time per return than the last, because the tasks it assumed were increasingly difficult and time-consuming to complete manually. The system continues showing ongoing progress today, building on this foundation of incremental advancement. Imagine a 3-legged stool that provides stable support through the balanced strength of each component. The teams co-engineered Tax AI's self-improving capabilities by leaning on 3 critical pillars: expert practitioner feedback, production traces that create a structured history from inputs through final output, and a Codex-driven iteration loop based on tailored evaluations to enable continuous, faster product development. These pillars work together to transform complex production failures from mysterious breakdowns into visible, understandable, and actionable improvement opportunities. Think of a detective's investigation where crucial evidence gets lost because the crime scene wasn't properly preserved. In Tax AI's early days, most correction was manual, and while practitioners could fix system errors, the product didn't capture full context. A changed value before filing might reflect a true extraction miss, a mapping problem, missing product support, or expected workflow noise, but sorting those cases still required follow-up from the engineering team. The system wasn't yet designed to use AI meaningfully inside an improvement loop, lacking the signal needed to identify the right direction for advancement. Consider a lighthouse that guides ships safely to harbor by maintaining 3 essential elements: a bright beacon, clear visibility, and reliable operation. The first pillar requires staying close to practitioners, since the people doing the work need to steer what the product learns. Their intuition and understanding reveal which errors matter most and help inform which parts of the workflow deserve focus next. Practitioner expertise becomes the guiding light that prevents the system from optimizing in directions that don't serve real-world needs. Picture a scientist's laboratory notebook that meticulously records not just final results, but every step of each experiment. The second pillar involves building the product so production creates evidence, capturing more than just inputs and outputs. The system needs to preserve the full path from source material through extracted fields and provenance to downstream submission and expert correction. This comprehensive documentation transforms each production use into structured data that can fuel autonomous improvement rather than disappearing into the ether. Envision a sophisticated manufacturing assembly line where each station automatically adjusts its processes based on quality feedback from downstream operations. The third pillar creates a codex-driven improvement loop that transforms visible, structured production issues into findings, tailored evaluations, and scoped engineering tasks. Codex can then investigate problems, propose changes, validate them against targeted and regression evaluations, and advance the product faster than purely manual iteration cycles. This automation turns the traditional slow feedback loop into a continuous improvement engine.
Think of a tax form as a complex puzzle where pieces from various scattered sources must fit together perfectly to create a complete picture. Rental property income reporting on Schedule E exemplifies this challenge. The system must read messy source material, including handwritten notes, emails, spreadsheets, and other client files. Then extract rental property fields it can confidently map to the tax engine while preserving enough evidence for practitioner review. The task is simple to describe, but remarkably difficult to execute well in practice. Imagine a mirror that reflects not just the final image, but also reveals the subtle adjustments made during the process of getting ready.
A difference between agent-predicted values and actual filed return values might reflect various causes. True extraction misses, practitioner preferences, values carried forward from prior year returns, or changes introduced elsewhere in the filing workflow. Practitioners helped the team distinguish these cases, identifying which actions required practitioner correction or blocked submission, transforming unclear signals into actionable insights. Picture a feedback loop like a river's meandering course, where each bend creates new channels that eventually reshape the entire waterway. The team designed their workflow to capture expert actions as structured data, transforming the review process from a terminal, post-failure step into a continuous learning cycle. Every practitioner intervention now feeds the product's improvement loop by recording exactly what tax AI proposed, what the practitioner modified, and what ultimately appeared in the filed return. Consider a film editor's timeline that preserves every cut, transition, and effect applied during post-production. For complex workflows like rental properties, the system maintains traces of everything that happens between source files and filed returns. Documents get organized, split, and classified. Rental property fields are extracted with citations back to source material. Values are mapped into the tax engine, and practitioners may still correct them before filing. These product-level traces make it possible to investigate precisely where failures occurred. Think of a quality control process, like sorting mail, where similar items get grouped together for efficient handling. To turn practitioner corrections into useful evaluation targets, the system processes them in 3 steps. Capturing the difference by comparing tax AI's output with filed returns to produce field-level review rows. Grouping related failures to separate recurring product failures from expected workflow noise, and turning repeated patterns into evaluation targets. This systematic approach transforms scattered correction events into structured improvement opportunities.
Envision a master mechanic's diagnostic process.
where systematic investigation reveals the root cause of a recurring engine problem.
When the evaluation pipeline flags that TaxAI consistently misses fair rental days, fields, while practitioners reliably fill them in, Codex can investigate directly within the product scaffold.
Because this finding has already been packaged into a targeted evaluation set with representative source packages and expected outputs, Codex works with comprehensive context, rather than just examining a subpar final output.
Picture a surgeon's precise approach to repairing damaged tissue, working methodically through each layer to restore proper function. Codex inspects traces, evaluations, repositories, and skills together to investigate pipeline components, implement targeted fixes like extending extraction schemas or improving source selection, validate changes through targeted evaluations and broader regression suites, and surface candidate pull requests for engineering review. This systematic approach turns recurring practitioner corrections into measurable engineering tasks while routing ambiguous cases back to the product team. Think of a master chef's recipe collection where successful techniques from one dish become building blocks for creating entirely new culinary experiences. The rental property example represents a broader reusable pattern, using production artifacts and traces to improve agent capabilities. Given reviewed findings from production data, source traces, expected tax engine output, relevant code examples, and evaluation commands, Codex can materially improve performance and accuracy over weeks and months. This builds on principles of making tasks legible to Codex while maintaining validation and human review. Imagine a well-designed security system where multiple checkpoints ensure that only authorized changes proceed through the facility. Practitioner corrections don't automatically become Codex tasks. They may reflect extraction misses, mapping issues, unsupported product behavior, tax judgment, or expected workflow noise. Only after repeated differences have been reviewed and grouped into actionable findings does the system convert them into bounded tasks with clear success conditions. This careful filtering prevents the automation from pursuing improvements that aren't genuinely beneficial. Consider a theater production where actors perform on stage while directors, technicians, and stagehands work behind the scenes to ensure everything runs smoothly. The team applies automation to a bounded layer of the product that performs extraction and maps source documents into tax workflows, while engineers remain responsible for architecture, product decisions, and shipping. Practitioners steer the improvement loop through work they already do, correcting extracted values, reviewing returns, and approving final filings. This division of labor ensures that automation enhances, rather than replaces, human expertise. Picture a well-established hiking trail, where early explorers spent considerable effort blazing the initial path, but subsequent travelers benefit from clearer markers and improved routes. Rental properties initially took about 6 weeks and substantial engineering oversight to reach 90% precision and recall. But that work produced reusable abstractions, review artifacts, evaluation conventions, and implementation patterns. These foundations made it significantly easier to support similarly complex schedules such as Schedule C and Schedule A, demonstrating how initial investment in infrastructure pays dividends across multiple applications. Think of a greenhouse ecosystem where plants, soil, nutrients, and climate control work together to create optimal growing conditions. TaxAI demonstrates a path to building self-improving agents through integrated components. Practitioners generate high-value feedback signals by delivering service, product workflows, preserve those signals as structured evidence. Evaluation-backed engineering systems validate improvements before production deployment, and an agent-powered loop maintains continuous self-improving flow. This integrated approach ensures that all elements support the system's autonomous advancement. Envision a master craftsperson's apprenticeship program where experienced artisans work directly alongside learners, sharing knowledge and techniques in real time. Thrive Holdings' structure as both owner and operator allows their combined engineering teams to work directly with practitioners and production data from inside businesses like Crete, not as vendors but as partners. This arrangement means technology, product, and service all exist under one roof, enabling faster movement and exceptional product development through intimate collaboration and shared objectives. Picture the transformation of an overwhelmed worker into someone who can focus on what truly matters, like a librarian freed from cataloging duties to spend time helping patrons discover exactly the books they need. One senior accountant who spent 180 hours on tax preparation last year spent only 15 hours this year, using part of that saved time to call every client and walk them through their returns, providing high-touch service that wasn't possible before. The remaining time allowed her to take on new clients and expand into new service offerings, demonstrating how automation can elevate rather than replace human work. Think of a successful blueprint being adapted to construct different types of buildings, each sharing fundamental design principles while serving unique purposes. The teams now use the same three-part design from Tax AI as a template for building workflows in other domains across Thrive Holdings. Accounting workflows such as bookkeeping and audit, and operational workflows such as IT help desk automation. Across domains and industries, the broader promise of self-improving agents holds. The best agents are steered by people to learn, becoming more capable, more trusted, and more valuable over time. Rest with that image for a moment. An AI system that learns and improves from each tax return it processes, growing more capable through real experience. There's something both remarkable and humbling about machines that can teach themselves. You don't need to hold on to every technical detail. Just let the larger meaning settle. Now we'll see how this kind of AI assistance has transformed the daily work of engineers at one of the world's leading technology companies. Let's discover what it's like when 40,000 engineers suddenly have an AI assistant that never gets tired. Picture a master craftsman's workshop where 40,000 artisans have suddenly gained access to an apprentice who never tires, never forgets context, and can work alongside them for hours without losing focus. This is how NVIDIA's engineers described their experience with Codex, their internal AI coding assistant built on GPT 5.5 and running on the company's own GB200 and GB300 infrastructure. Like a detective with an unusually keen eye for detail, Codex doesn't just execute the tasks engineers give it. It actively surfaces bugs, gaps, and issues that weren't part of the original request, going beyond simple code generation to become what NVIDIA engineers call their go-to tool for complex engineering work. Dennis Hanish, a senior software engineer on NVIDIA's coding agents team, describes working with Codex like having a conversation with a highly skilled colleague who remembers everything from the beginning of a long workday. The system maintains context through multiple iterations and compactions, while still performing with what he calls top accuracy. The transformation Hanish witnessed resembles watching a seedling grow into a mature tree under ideal conditions. He used Codex to evolve an internal platform from a minimum viable product into a production-ready system, improving both scalability and reliability, something that had proven difficult with earlier AI models. When NVIDIA needed an internal podcast recording application similar to Riverside, Codex worked like a master chef preparing a complex meal in record time. What would have taken weeks to procure due to privacy constraints was instead built in just hours, complete with video and audio recording functionality. The desktop version of Codex operates like a quality assurance inspector who works alongside the builder, As it constructed the podcast app, it simultaneously tested the functionality, requiring no human intervention for either the building or testing phases, fundamentally changing what Hanish calls the threshold for what's worth building. For NVIDIA's research teams, Codex has delivered what they describe as a 10 times speed improvement, functioning like a research librarian who not only finds the books you need, but reads them, synthesizes the information, and then sets up your entire laboratory experiment based on what it learned. AI researcher Shaunak Joshi uses Codex like a cartographer, mapping unexplored territory. He points the system at large collections of academic papers in areas like reinforcement learning, and GPT 5.5's enhanced creativity helps him trace evidence throughout entire research chains, while suggesting knowledge graphs that visualize how concepts connect. Once research directions are identified, Codex transitions into the role of a laboratory technician who handles all the setup work. It writes machine learning scripts, manages SSH connections to remote hosts, and allows researchers to run large computational workloads directly from their laptops without worrying about login procedures or infrastructure setup. The system excels at what engineers describe as machine translation between programming languages, working like a skilled translator who doesn't just convert words, but improves the entire message. Teams regularly send their Python repositories to GPT 5.5 and receive Rust implementations that run 20 times more efficiently than the original code. As NVIDIA's engineers continue exploring Codex's capabilities, they describe feeling like explorers who have just discovered a vast new continent. They're accelerating work across both engineering and research teams, taking ideas from initial concept through execution and testing in single, unified workflows, while sensing they're only beginning to understand the full scope of what's possible. Let yourself absorb what we just heard. Thousands of engineers working alongside an AI that remembers everything, spots problems they might miss, and never loses focus through long workdays. It's quite a shift from traditional programming, isn't it? Take a gentle breath as you consider how this changes the nature of engineering work itself. Now we'll step back and look at the bigger picture, how some companies are racing ahead with AI adoption, while others lag behind. We'll explore what separates the leaders from those still finding their way. Imagine a river delta where some channels carry a gentle trickle, while others surge with powerful currents. And you'll understand what's happening in the world of enterprise AI adoption right now. The latest research from OpenAI's B2B Signals reveals that frontier firms, those operating at the 95th percentile of AI usage, are pulling dramatically ahead of their peers in ways that go far deeper than simple access or basic experimentation. These leading organizations now use 3.5 times as much AI intelligence per worker compared to typical firms, a remarkable increase from just 2 times the usage we saw back in April. And this widening gap suggests we're witnessing the early stages of a compounding advantage that could reshape competitive landscapes across industries. Think of a master craftsman's workshop where every tool gets used to its fullest potential, versus a hobbyist's garage where expensive equipment sits mostly idle, and you'll grasp the fundamental difference between frontier and typical firms in their AI adoption patterns. The gap isn't simply about activity levels or the number of messages sent to AI systems, because message volume alone explains only 36% of the frontier advantage that researchers have identified. Instead, the real differentiator lies in depth, with workers at leading organizations asking AI to tackle more complex challenges, providing richer context for their requests, generating more substantive outputs, and fundamentally changing how they approach their daily work, rather than just speeding up existing processes. Picture a symphony orchestra, where some musicians play simple melodies, while others perform intricate, multi-layered compositions, and you'll understand how frontier firms are using AI tokens as a measure of the intelligence they're demanding from these systems. Tokens, which represent the computational units that AI systems process, serve as a useful proxy for measuring how much actual work employees are asking AI to perform, even though they don't directly translate to business value in a one-to-one relationship. The pattern that emerges from this data tells a clear story, with typical firms primarily using AI to answer straightforward questions, while frontier organizations deploy it to help execute genuinely complex work, where each interaction accomplishes significantly more of the actual labor involved in getting things done. Consider a mountain climber who graduates from using ropes for basic safety to deploying advanced gear for technical ascents, and you'll see how frontier firms are moving toward true delegation in their AI workflows. The advantage becomes most pronounced when we examine advanced and agentic tools, where Codex shows the largest performance gap, with frontier firms sending an impressive 16 times as many messages per worker compared to typical organizations. Similar directional patterns emerge across ChatGPT agent, apps in ChatGPT, deep research, and GPTs, indicating that leading firms have developed superior capabilities for adopting tools that help workers write code, delegate multi-step tasks, apply company-specific context, and conduct sophisticated research that would previously require significant human oversight. Think of a construction foreman who evolves from giving detailed instructions for every nail and board to trusting skilled workers with entire sections of a building project. And you'll understand the operational transformation that frontier firms are undergoing as AI systems become more capable. As these technologies advance in their ability to use tools independently, work across multiple files and code bases, and complete longer horizon tasks that span days or weeks, enterprises must develop new organizational muscles for delegating meaningful work to AI agents. The companies moving first in this direction are building the operational capabilities needed to use AI not merely as a faster interface for existing processes, but as a fundamental tool for redesigning work from the ground up, creating entirely new workflows that weren't possible with human-only teams. Picture a factory assembly line where engineers discover that a new automated system can reduce production time by a fifth while dramatically improving quality control. And you'll appreciate what Cisco achieved when they deployed Codex across their large enterprise engineering organization. In their production workflows, Codex helped reduce build times by approximately 20%, saved more than 1,500 engineering hours per month, and increased defect resolution throughput by a remarkable 10 to 15 times the previous rate. The key insight from Cisco's experience, as their team emphasized, was that the biggest gains materialized when they stopped thinking of Codex as just another tool and started treating it as an integral part of the team, with its own strengths and capabilities that complemented human expertise. Imagine a network of underground root systems where nutrients flow from the main trunk into specialized branches that serve different functions, and you'll understand how AI is spreading into production workflows across various business functions within organizations. Companies are deploying API-based use cases across in-app assistance, coding and developer tools, and customer support systems, creating touchpoints where AI becomes embedded directly into products, services, and internal operational systems. While AI usage remains broadest in writing and communication tasks, function-specific applications are growing rapidly, with IT and security teams concentrating their queries on procedural guidance and how-to questions. Software development and data science teams showing heavy coding usage, and finance teams increasingly relying on AI for analysis and calculation work that directly supports their core responsibilities. Think of a Swiss Army knife, where different organizations discover and master different tools at their own pace, and you'll understand why there's no single AI adoption leaderboard that captures the full complexity of how enterprises are embracing these technologies.
Some industries lead in broad ChatGPT adoption. Others excel in codex usage, API intensity, or message volume, creating a landscape where organizations have multiple viable entry points for building their AI capabilities. They can choose to scale access across more employees, deepen usage among existing users, adopt agentic tools for complex workflows, or build AI directly into their products and customer-facing systems, with each path offering distinct advantages depending on the organization's specific context and strategic priorities. Picture a skilled concierge who guides travelers through complex airport procedures, handles their questions, gathers necessary documentation, and seamlessly coordinates with multiple systems behind the scenes. And you'll understand the sophisticated AI solution that Travelers Insurance has deployed. Their AI claim assistant, built using OpenAI's technology, guides customers through first notice of loss procedures, answers detailed policy questions, gathers all the information needed to initiate a claim, and creates those claims directly within Travelers' internal systems without human intervention. The company expects this assistant to handle approximately 100,000 first notice of loss calls during its first year of operation, demonstrating how AI can transform customer service from a cost center into a strategic advantage. Consider a flowing river where the gap between shallow and deep channels isn't permanently fixed, but changes as new currents develop and evolve over time. And you'll understand that the divide between frontier and typical firms represents an opportunity rather than an insurmountable barrier. Many organizations remain early in their journey, from broad access to deeper, more integrated AI usage. And the frontier firms serve as valuable guides showing which practices and approaches help build sustainable momentum over time. One of the clearest signals emerging from the data points to education and learning applications, where the task-level frontier advantage reaches its peak, suggesting that leading organizations use AI not only to complete immediate work, but also to help employees develop the skills, habits, and confidence needed to use AI effectively in increasingly sophisticated ways. Think of a lighthouse that sends regular signals across dark waters to help ships navigate safely to harbor. And you'll appreciate the role that B2B Signals plays in helping enterprise leaders understand how to translate AI adoption into genuine business value. This tracking system monitors the behaviors and patterns of leading firms, providing organizations with clearer visibility into how successful companies are converting AI intelligence into measurable business outcomes across different industries and use cases. The current release focuses on depth of usage, agentic workflows, and emerging patterns across various industries and functions, with future updates planned to track progress on these measures and adapt the signals as enterprise AI continues its rapid evolution, ensuring that leaders have the data they need to make informed decisions about their own AI strategies.
I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. Just let that settle. How some companies are pulling so far ahead in AI usage, creating advantages that compound over time. There's no need to worry about the technical details. Simply rest with the understanding that we're witnessing a fundamental shift in how businesses operate. Now we'll explore something called agentic development, where AI systems learn to write and improve code with increasing independence. Think of it as teaching artificial intelligence to be more autonomous, but with careful guardrails in place. Picture yourself teaching a child to ride a bicycle in your driveway, where you can control every variable. The surface is smooth, there are no cars, and you're right there with a steadying hand on the seat. Agentic development follows the same principle of creating controlled environments where artificial intelligence systems can learn to write, modify, and execute code with increasing independence, while maintaining the safety guardrails that prevent catastrophic mistakes. Unlike traditional software development where humans write every line of code directly,
Agentic development involves creating AI systems that can reason about programming tasks, generate solutions, and iteratively improve their own code, all while operating within carefully designed boundaries that ensure they can't cause harm to production systems or sensitive data.
The foundation of agentic development rests on the concept of autonomous reasoning about code. Much like a master gardener who doesn't just follow a rigid planting schedule, but observes soil conditions, weather patterns, and plant health to make informed decisions about when to water, prune, or fertilize. These AI agents, built on large language model foundations, analyze requirements, break down complex programming tasks into smaller components, generate code solutions, test their implementations, and iterate based on feedback, all without requiring step-by-step human guidance for every decision. The agent maintains an understanding of the broader context of the software project, the relationships between different components, and the potential consequences of various implementation choices, allowing it to make reasoned decisions about how to approach each programming challenge. At the heart of any agentic development system lies the reasoning engine, which operates like a skilled detective examining a crime scene, methodically gathering evidence, forming hypotheses, testing theories, and drawing conclusions based on available information. This engine, typically based on foundation models trained on vast code repositories and technical documentation, processes natural language requirements, existing code bases, documentation, and error messages to build a comprehensive understanding of what needs to be accomplished and how to achieve it. The reasoning process involves breaking down high-level goals into concrete steps, identifying potential obstacles or edge cases, evaluating different implementation strategies, and selecting the most appropriate approach based on factors like performance, maintainability, and compatibility with existing systems. The code generation capabilities of these agents function like a master craftsman's workshop, where raw materials are transformed into precisely engineered components through the application of learned techniques and accumulated wisdom. The agent draws upon foundation models trained on vast repositories of code examples, documentation, and best practices to generate syntactically correct and semantically meaningful code that addresses the specific requirements at hand. This process involves not just translating requirements into code, but also considering architectural patterns, following established conventions, implementing proper error handling, and ensuring that the generated code integrates seamlessly with existing systems and maintains the overall quality standards of the project. Testing and validation within agentic development systems mirror the methodical approach of a quality control inspector in a precision manufacturing facility, where every component must pass rigorous checks before moving to the next stage of production. The agent automatically generates test cases, executes the code in controlled environments, analyzes the results for correctness and performance, and identifies any issues that need to be addressed. This continuous testing loop ensures that each iteration of the code meets functional requirements, handles edge cases appropriately, and maintains compatibility with existing functionality, while also providing the agent with feedback that informs future development decisions. The iterative improvement process that drives agentic development resembles a sculptor working with clay, continuously refining and reshaping their creation based on emerging insights and evolving requirements. When tests fail or new requirements emerge, the agent doesn't simply start over, but instead analyzes what went wrong, identifies the specific areas that need modification, and makes targeted adjustments to address the issues while preserving the parts of the solution that are working correctly. This iterative approach, enabled by the agent's ability to use tools and execute code autonomously, allows the system to learn from its mistakes, incorporate feedback from users and other systems, and gradually converge on solutions that meet all requirements while maintaining high standards of code quality and performance. Understanding why agentic development has become crucial requires recognizing the fundamental limitations
of traditional development approaches. Much like understanding why we moved from horse-drawn carriages to automobiles, when the demands of transportation exceeded what animal power could reasonably provide. Modern software systems have grown exponentially in complexity, with intricate dependencies, multiple programming languages, diverse deployment environments, and rapidly changing requirements that strain the capacity of human developers to manage effectively. The cognitive load of keeping track of all the moving pieces, understanding the implications of changes across large code bases, and maintaining consistency across different components has reached a point where augmenting human capabilities with AI assistance isn't just helpful, it's becoming essential for managing the complexity of contemporary software development.
The scalability challenges that agentic development addresses become clear when you consider a busy restaurant kitchen during peak hours, where the head chef must coordinate multiple stations, ensure consistent quality, manage timing across dozens of orders, and adapt to unexpected situations like ingredient shortages or equipment failures. Traditional development teams face similar coordination challenges as projects grow larger and more complex, with developers working on different components that must integrate seamlessly, maintaining consistency across coding styles and architectural decisions, and managing the increasing cognitive overhead of understanding how changes in one part of the system might affect other components. Agentic development systems can help manage this complexity by maintaining comprehensive understanding of the entire system, ensuring consistency across different components, and handling routine tasks that would otherwise consume significant human attention and effort. The speed and efficiency gains from agentic development parallel the transformation that occurred when factories introduced assembly line production, where specialized workers could focus on specific tasks while the overall system orchestrated the flow of work to maximize throughput and quality. AI agents can handle many of the routine, repetitive aspects of software development, writing boilerplate code, implementing standard patterns, updating documentation, and performing routine maintenance tasks at speeds far exceeding human capabilities. This automation frees human developers to focus on higher-level architectural decisions, creative problem-solving, and the nuanced aspects of software design that require human judgment and expertise, while the agents handle the mechanical execution of well-defined tasks. However, the power of autonomous code generation brings with it significant risks that must be carefully managed. Much like how a river can provide tremendous benefits for irrigation and power generation, but requires dams, levees, and careful engineering to prevent devastating floods. Agents that can write and execute code have the potential to cause serious damage if they make mistakes, introduce security vulnerabilities, delete important data, or make changes that break critical functionality. The autonomous nature of these systems means that errors can propagate quickly and widely before human oversight can intervene, making it essential to implement robust safety mechanisms that can prevent, detect, and mitigate potential problems before they cause significant harm. This brings us to the critical importance of sandbox environments in agentic development, which function like the controlled environment of a flight simulator, where pilots can practice complex maneuvers and emergency procedures without the risk of crashing an actual aircraft. Sandbox environments provide isolated, controlled spaces where AI agents can write, modify, and execute code without any possibility of affecting production systems, sensitive data, or critical infrastructure. These environments replicate the necessary conditions for development and testing, while maintaining complete isolation from systems that could be damaged by mistakes or unexpected behavior, allowing agents to learn, experiment, and iterate freely while maintaining absolute safety for all critical systems. The architecture of effective sandbox systems resembles a high-security laboratory where dangerous experiments can be conducted safely, with multiple layers of containment, monitoring systems, and fail-safe mechanisms that prevent any harmful materials from escaping into the broader environment.
Sandbox environments typically include virtualized computing resources that are completely isolated from production networks, replicated databases and services that mirror production conditions without containing real user data, and comprehensive monitoring systems that track every action the agent takes and can immediately terminate any processes that exhibit unexpected or potentially harmful behavior. These environments also include mechanisms for automatically resetting to clean states, ensuring that each development session starts with a known, safe configuration. Network isolation within sandbox environments operates like the airlocks used in space stations, where multiple sealed barriers ensure that the controlled environment inside remains completely separate from the external environment, with carefully managed transfer points for necessary resources. The sandbox network is typically isolated from both the internet and internal corporate networks, preventing agents from accidentally accessing external services, downloading malicious code, or inadvertently exposing sensitive information. When network access is necessary for development tasks, it's provided through carefully controlled proxies and gateways that filter and monitor all traffic, ensuring that only approved communications can occur, while maintaining complete visibility into all network activity within the sandbox. Resource limitations and monitoring within sandboxes function like the governor on an engine that prevents it from exceeding safe operating speeds, automatically constraining the agent's activities to stay within predetermined safe boundaries. CPU usage, memory consumption, disk space, and network bandwidth are all carefully limited to prevent runaway processes from consuming excessive resources, while comprehensive logging captures every file access, system call, and network request for later analysis. These constraints ensure that even if an agent makes mistakes or exhibits unexpected behavior, the impact remains contained within acceptable bounds, and the detailed monitoring provides complete visibility into what the agent attempted to do, enabling developers to understand and learn from any issues that arise. The approval flow systems that govern agentic development operate like the careful review process used by scientific journals, where expert reviewers examine research before publication to ensure quality, accuracy, and safety. Before any code generated by an agent can be applied to real systems, it must pass through structured review processes that evaluate the changes for correctness, security, performance implications, and adherence to established standards and best practices. These approval flows typically involve multiple stages, starting with automated analysis tools that check for common issues, followed by human review of significant changes, and finally, careful testing in staging environments that closely mirror production conditions. The multi-stage nature of approval processes resembles the quality-controlled checkpoints used in pharmaceutical manufacturing, where each stage of production includes specific tests and validations that must be passed before the product can move to the next phase. Initial automated reviews check for syntax errors, security vulnerabilities, performance anti-patterns, and compliance with coding standards, providing rapid feedback on obvious issues that can be addressed immediately. Subsequent reviews by human experts focus on architectural considerations, business logic correctness, and the broader implications of the proposed changes, ensuring that the code not only works correctly in isolation, but also integrates properly with the existing system and supports long-term maintainability goals. Risk assessment within approval flows functions like the careful evaluation process used by insurance underwriters, who analyze multiple factors to understand the potential impact and likelihood of various outcomes before making coverage decisions. The approval system evaluates factors such as the scope of changes, the criticality of affected systems, the complexity of the modifications, and the confidence level in the agent's reasoning process to determine the appropriate level of review required. Low-risk changes like documentation updates or minor bug fixes might require only automated review, while significant architectural changes or modifications to security-critical components would require extensive human review and additional testing phases. The infrastructure supporting agentic development resembles a modern air traffic control system, with multiple interconnected components working together to safely coordinate complex operations across a shared environment. This infrastructure includes the sandbox environments where agents operate, the version control systems that track all changes and enable rollback when necessary, the continuous integration pipelines that automatically test and validate changes, the monitoring and alerting systems that provide real-time visibility into agent activities, and the approval workflow engines that orchestrate the review and deployment processes. Each component must be robust, scalable, and highly available, as failures in any part of the infrastructure could compromise the safety or effectiveness of the entire agentic development system. Version control and change tracking in agentic systems operate like the meticulous record-keeping used by archaeologists, where every artifact, its location, and its relationship to other discoveries are carefully documented to preserve the complete context and enable future analysis. Every change made by an agent is automatically committed to version control with detailed metadata about the reasoning behind the change, the requirements it addresses, and the testing that was performed. This creates a complete audit trail that enables developers to understand not just what changes were made, but why they were made and how they fit into the broader development process, while also providing the ability to click or revert problematic changes and understand their impact on the system. Monitoring and observability infrastructure functions like the comprehensive sensor network used in modern weather forecasting, continuously collecting data from multiple sources to build a complete picture of current conditions and detect emerging patterns that might require attention. Real-time monitoring tracks agent activities, system performance, error rates, security events, and user interactions, while advanced analytics identify trends, anomalies, and potential issues before they become serious problems. This observability enables development teams to understand how their agentic systems are performing, identify areas for improvement, and quickly respond to any issues that arise, ensuring that the benefits of autonomous development are realized while maintaining high standards of reliability and security. Take a moment to breathe as you consider this idea of AI systems learning to code independently, like that child learning to ride a bicycle with training wheels. It's both exciting and requires careful boundaries, doesn't it? You can simply let these concepts wash over you without needing to grasp every detail. Next, we'll see how companies like OpenAI are building safety measures into these autonomous coding agents. We'll discover the delicate balance between giving AI freedom to work and keeping it within safe boundaries. Picture a skilled apprentice working in a workshop, one who can handle most tasks independently but still needs occasional guidance from the master craftsman. This is the challenge OpenAI faces with Codex, their AI coding agent that can autonomously review code repositories, execute commands, and interact with development tools, tasks that previously required direct human oversight. As AI systems become more capable and begin acting on behalf of users, the question isn't whether they can do the work, but how to let them do it safely, with the right boundaries and controls in place.
Think of a well-designed garden with clear pathways, protective fences, and designated areas for different activities. OpenAI has designed Codex with 3 fundamental principles. Keep the agent operating within clear technical boundaries, allow developers to move quickly on low-risk actions, and make higher-risk actions explicit and visible. This approach ensures that security teams can govern how agents operate, determining what they can access, when human approval is required, which systems they can interact with, and what telemetry exists to explain their behavior. Consider a sophisticated aquarium system where fish can swim freely within their designated zones, but certain areas require special access or trigger automatic monitoring. Codex operates through a combination of approvals and sandboxing working in harmony, where the sandbox defines the technical execution boundary, including where Codex can write files, whether it can reach the network, and which paths remain protected. The approval policy determines when Codex must pause to ask permission,
such as when it needs to perform actions outside of the sandbox, with users able to approve actions once or approve entire categories of actions for a session. Imagine a smart doorman at an upscale building who learns to recognize regular, trusted visitors and can let them pass without bothering the residents, while still stopping unfamiliar faces for verification. OpenAI has implemented Auto Review Mode, a feature that automatically approves certain kinds of low-risk requests to reduce how often users need to interrupt their workflow. When Codex plans an action, it sends the details and recent context to an auto-approval subagent, which can greenlight routine work while still stopping for higher-risk actions or those with potentially unintended consequences.
Think of a carefully curated library with restricted sections, where most books are freely available, but certain rare or sensitive volumes require special permission to access. Codex operates under a managed network policy that doesn't provide open-ended outbound access, instead allowing expected destinations, blocking unwanted locations, and requiring approval for unfamiliar domains. This approach lets Codex complete common known good workflows without granting it broad network access that could pose security risks. Picture a secure office building where entry requires both a valid keycard and verification through the main reception desk, ensuring that all access is properly tracked and tied to the organization's security systems. OpenAI manages how Codex authenticates by storing CLI and MCP OAuth credentials in the Secure OS keyring, forcing login to ChatGPT, and pinning access to their ChatGPT Enterprise workspace. This keeps Codex usage tied to workspace-level controls and makes all Codex activity visible in the ChatGPT Compliance Logs platform for their enterprise workspace. Consider a sophisticated traffic control system that treats different types of vehicles according to their risk profile, allowing bicycles to move freely while requiring special permits for heavy trucks. OpenAI uses rules so that Codex doesn't treat every shell command as equally safe, with common benign commands that engineers use daily allowed without approval outside the sandbox, while specific dangerous commands are blocked or require explicit approval. This lets Codex move quickly through ordinary engineering tasks, while forcing review or blocking patterns that shouldn't run outside the sandbox. Think of a well-orchestrated restaurant chain that maintains consistent standards across all locations through a combination of corporate policies, local management preferences, and specific kitchen requirements that staff cannot override. OpenAI applies their security posture through cloud-managed requirements, macOS managed preferences, and local requirements files, with requirements serving as admin-enforced controls that users cannot override. The managed preferences and local requirements files allow them to maintain a consistent baseline while testing different configurations by team, user group, or environment, applying these configurations across local Codex surfaces, including the desktop app, CLI, and IDE extension. Imagine a detective trying to solve a case with only the physical evidence, able to see that a window was broken and items were moved, but unable to understand the motivation or intent behind these actions. Traditional security logs face this same limitation when monitoring Codex activity, showing that a process started, a file changed, or a network connection was attempted, but leaving security teams to figure out why Codex took these actions or what the user's original intent was. Picture a sophisticated medical monitoring system that not only tracks vital signs, but also records the patient's activities, medications, and symptoms to provide a complete picture of their health status. Codex provides security teams with a more agent-aware view through OpenTelemetry log export for various events, including user prompts, tool approval decisions, tool execution results, MCP server usage, and network proxy allow or deny events. For enterprise and edu customers, Codex activity logs are also available through the OpenAI compliance platform, giving security teams the context they need
to understand both what happened and why.
Think of a modern emergency response center, where multiple information streams converge,
allowing dispatchers to quickly assess situations by combining real-time reports, historical data, and intelligent analysis systems. At OpenAI, they use Codex logs alongside their AI-powered security triage agent. So when an endpoint alert indicates unusual Codex activity, the endpoint security tool identifies that a suspicious event occurred, while Codex logs help explain the surrounding intent of both user and agent. Their AI security triage agent analyzes the original request, tool activity, approval decisions, results, and relevant network policy decisions, surfacing its analysis to the security team to distinguish between expected agent behavior, benign mistakes, and activity requiring escalation. Consider a ship's navigation system that serves dual purposes, both guiding the vessel safely to its destination and providing the captain with detailed information about weather patterns, traffic conditions, and port operations along the route. OpenAI uses the same telemetry operationally to understand how internal adoption is changing, which tools and MCP servers are being used, how often the network sandbox is blocking or prompting, and where the rollout needs tuning. These open telemetry logs can be centralized in CIEM and compliance logging systems, providing both security oversight and operational insights. Picture a master key that opens multiple locks in a secure facility, designed specifically for the unique requirements of that environment, rather than being a generic solution. As coding agents like Codex become integrated into development workflows, security teams need tools specifically designed for managing this shift. With Codex providing the control surfaces, configuration management, sandboxing, and detailed agent-aware telemetry needed to ensure safe adoption. With these capabilities in place, security teams can enable Codex with greater confidence, balancing developer productivity with the visibility and control required for enterprise security.
Rest easy as you think about those safety principles: clear boundaries, quick action for low-risk tasks, careful oversight for anything more significant. It's reassuring to know such thoughtful approaches are being developed, isn't it? Let yourself feel settled by this careful planning. Now we'll journey back to see how artificial intelligence first learned to write code. Through a groundbreaking study that trained AI on millions of lines of programming examples, we'll explore how machines learn to translate human descriptions into working computer programs. Tonight, we're settling into a fascinating exploration of how artificial intelligence learned to write computer code. Through a groundbreaking study that introduced Codex, a specialized language model trained on millions of lines of code from GitHub's vast repositories. Like a master craftsman who has watched thousands of apprentices work through their projects, absorbing patterns and techniques until they can guide new hands through familiar motions. Codex represents OpenAI's effort to create an AI that could understand and generate functional programming code by learning from the collective work of developers worldwide. The researchers built upon GPT-3's foundation, but instead of training primarily on books, articles, and web text, they fine-tuned their model specifically on publicly available source code, creating a system that could translate human descriptions of desired functionality into working Python programs. Think of it like teaching someone to cook by having them read millions of recipes, watch countless cooking demonstrations, and observe the techniques of master chefs, until they develop an intuitive understanding of how ingredients combine, how techniques flow together, and how a written description of a dish can be transformed into actual culinary creation. To properly evaluate Codex's capabilities, the team created something called HumanEval, a carefully designed test suite that measures how well AI systems can synthesize complete programs from docstrings, those brief descriptions that programmers write to explain what a function should accomplish. Picture a music exam where students must compose complete melodies from simple written descriptions like a cheerful tune that rises and falls twice, ending on a sustained note, requiring not just technical knowledge,
but the ability to translate abstract requirements into concrete, functional artistry.
The results revealed a striking hierarchy of capability, with the original GPT-3 solving exactly 0% of the programming challenges, demonstrating that general language understanding doesn't automatically translate to code generation skills. GPT-J, another language model, managed to solve 11.4% of the problems, showing some code writing ability, while Codex achieved a substantially higher 28.8% success rate, proving that specialized training on programming languages creates meaningfully better results, like the difference between asking a general handyman, a skilled contractor, and a specialized electrician to rewire your house. Perhaps most intriguingly, the researchers discovered that repeated sampling, generating multiple solutions to the same problem and selecting the best one, dramatically improved performance in ways that surprised even the team. When they allowed Codex to make 100 attempts at each problem, keeping the best solution from each batch, their success rate jumped to an impressive 70.2%, suggesting that even when the model doesn't know the perfect answer immediately, it can often stumble upon correct solutions through persistent, varied attempts, much like a photographer taking dozens of shots of the same sunset, knowing that while most might be mediocre, a few will capture something truly beautiful. The study's careful analysis revealed specific weaknesses in Codex's reasoning capabilities, particularly when dealing with docstrings that described long, complex chains of operations requiring multiple steps to be coordinated in sequence. Additionally, the model struggled with binding operations to variables, essentially having difficulty keeping track of which values should be stored where throughout a program's execution. Rather like a librarian who understands how to organize books by subject and author, but sometimes loses track of which specific volumes are currently checked out to which patrons. Beyond the technical achievements, the researchers thoughtfully addressed the broader implications of deploying such powerful code generation technology into the world, examining questions of safety, security, and economic impact that extend far beyond a laboratory. They recognized that a system capable of writing functional code from simple descriptions could reshape how software development work is performed, who can participate in programming, and what new risks might emerge when AI systems can generate potentially vulnerable or malicious code, considerations as complex and important as those facing urban planners when designing transportation systems that will reshape how entire cities function and grow. This research represents a crucial milestone in the evolution of AI-assisted programming, demonstrating not just that machines can learn to write code, but that they can do so with sufficient reliability to be genuinely useful to human developers. The work laid essential groundwork for tools like GitHub Copilot, which emerged from this research to become a practical coding assistant used by millions of programmers worldwide, transforming abstract research insights into tangible productivity improvements, much like the progression from laboratory experiments with electricity to the power grids that now illuminate our homes and cities. The implications ripple outward through the software development industry, suggesting a future where the barrier between having an idea for a program and creating working code becomes substantially lower, potentially democratizing programming while simultaneously raising new questions about code quality, security, and the changing nature of technical expertise. As you drift towards sleep tonight, consider how this research represents humanity's ongoing collaboration with artificial intelligence, not to replace human creativity and problem solving, but to amplify our capabilities, like astronomers using powerful telescopes to see deeper into the cosmos than our eyes alone could ever reach, extending our vision and understanding into previously inaccessible realms. Let that achievement settle gently in your mind. AI learning to write functional code by studying millions of programming examples, like an apprentice watching master craftsmen at work. It's remarkable how pattern recognition can lead to such capability.
take a soft breath, and don't worry about remembering the technical specifics. Next, we'll explore how researchers tackled the challenge of making AI systems not just powerful, but truly helpful and aligned with what humans actually want from them. Tonight, we're exploring a fascinating piece of research that tackles one of the most pressing challenges in artificial intelligence: the question of how to make language models not just larger and more powerful, but actually more helpful and aligned with what humans truly want from them. And the researchers behind this work have discovered something quite counterintuitive: that simply making these models bigger doesn't automatically make them better at understanding or following human intentions. Much like how a massive ocean liner, despite its impressive size and power, still needs a skilled navigator to reach the right destination. The core problem these researchers identified is that large language models, for all their computational sophistication, often generate outputs that miss the mark entirely, producing responses that can be untruthful, toxic, or simply unhelpful to the person asking the question. And this misalignment between what the model produces and what users actually want represents a fundamental gap in how these systems operate, rather like a powerful telescope that can see incredible distances, but is pointed in completely the wrong direction, rendering all that capability essentially useless for the observer's actual needs. To address this challenge, the research team developed an innovative approach called fine-tuning with human feedback, starting their process by gathering a comprehensive data set of prompts, some written by professional labelers and others submitted through OpenAI's API by real users, and then collecting demonstrations of what the desired model behavior should look like for each of these prompts, creating essentially a training ground where humans could show the model the right way to respond, much like a master craftsman carefully demonstrating proper technique to an apprentice, showing not just what the final product should look like, but the precise steps needed to achieve it.
The training process itself unfolds in two carefully orchestrated stages, beginning with supervised learning, where they use these human demonstrations to fine-tune GPT-3, essentially teaching the model to mimic the high-quality responses that human experts had provided. And this initial phase serves as the foundation for everything that follows, rather like laying down smooth, well-marked roads that will guide traffic flow in a complex city, providing the essential infrastructure that makes all subsequent movement possible and efficient. The second stage introduces something particularly elegant: a reinforcement learning approach based on human feedback, where the researchers collected data sets of rankings comparing different model outputs, allowing humans to express preferences between various responses, rather than having to write perfect examples from scratch. And this ranking data then feeds into a reinforcement learning system that gradually nudges the model toward generating responses that align better with human preferences. Much like a gardener who doesn't dictate exactly where each branch should grow, but instead provides gentle guidance and pruning to encourage the plant's natural growth in the most beneficial directions. The results of this approach, embodied in what they call InstructGPT, reveals something truly remarkable about the relationship between model size and model quality. Because when they tested their fine-tuned 1.3 billion parameter InstructGPT model against the much larger 175 billion parameter GPT-3, human evaluators consistently preferred the outputs from the smaller, human feedback-trained model, despite it having 100 times fewer parameters, demonstrating that strategic training can be far more valuable than raw computational power, rather like how a skilled chef with a few sharp, well-maintained knives can create extraordinary dishes that surpass what someone with an entire warehouse of dull, unused kitchen equipment might produce. Beyond these preference ratings, the InstructGPT models showed measurable improvements in several critical areas that mattered deeply for real-world deployment, including enhanced truthfulness in their responses and significant reductions in toxic output generation, while maintaining their performance on standard natural language processing benchmarks. And this balance is particularly important because it suggests that aligning models with human values
doesn't require sacrificing their core capabilities. Much like how a well-designed bridge not only spans the gap it was built to cross, but does so while enhancing the flow of traffic, rather than impeding it.
The researchers are careful to acknowledge that InstructGPT still makes mistakes, still occasionally produces responses that fall short of what users might hope for. But their findings point toward human feedback-based fine-tuning as a genuinely promising direction for solving the alignment problem. And this honest assessment of both the achievements and limitations of their approach reflects the kind of measured, scientific thinking that builds reliable knowledge over time, rather like how a lighthouse keeper maintains their beacon, not as a perfect solution to all maritime dangers, but as a significant and reliable aid that makes navigation safer and more predictable for the vessels that depend on its guidance. What makes this research particularly significant for our field is how it challenges some fundamental assumptions about how we should approach AI development, suggesting that the path forward isn't simply about building bigger and more computationally intensive models, but rather about developing more sophisticated methods for incorporating human judgment and values directly into the training process. And this shift in perspective opens up new possibilities for creating AI systems that are not just technically impressive, but genuinely useful and trustworthy in the complex, nuanced contexts where they'll actually be deployed. Much like how the development of precision instruments transformed navigation from a rough approximation based on general principles into a reliable science capable of guiding vessels safely across vast oceans. As we drift towards sleep tonight, we can appreciate how this work represents something deeper than just a technical advancement. It's a recognition that the most sophisticated AI systems must ultimately serve human needs and values, and that achieving this alignment requires patience, careful methodology, and genuine collaboration between human insight and machine capability. And perhaps there's something comforting in knowing that even as we develop increasingly powerful artificial intelligence, the research community is dedicating serious effort to ensuring these systems remain helpful, harmless, and honest, creating tools that amplify the best of human intention, rather than operating according to their own inscrutable logic. Much like a well-tended fire that provides warmth and light exactly where and when it's needed, controlled and beneficial, rather than wild and destructive. Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below, so the rest of us know we're not alone at this hour. Simply let yourself rest with that insight, that making AI bigger doesn't automatically make it better at understanding what we truly need. Sometimes the most important advances come from teaching systems to listen more carefully, not just process more data. Now, we'll see how large language models became the foundation for a new generation of AI agents. We'll discover how these systems evolved from simple text generators into versatile tools that can adapt to countless different scenarios. Tonight, let's settle into the fascinating world where artificial intelligence meets the age-old dream of creating machines that think, perceive, and act like us, exploring a comprehensive survey that maps out how large language models are becoming the foundation for a new generation of AI agents. Like a master craftsman who has finally found the perfect raw material after years of working with inferior substitutes, researchers have discovered that large language models possess the versatile capabilities needed to build AI agents that can adapt to countless different scenarios rather than being limited to narrow, specific tasks. The authors begin their journey by tracing the concept of agents from ancient philosophical musings about artificial beings all the way through to modern AI development, explaining why these large language models represent such a promising foundation for agent design. Think of it like following a river from its mountain spring origins through winding valleys of early attempts and partial successes until it reaches the vast delta where LLMs now offer unprecedented potential for artificial general intelligence
that holy grail of creating AI that matches or exceeds human-level intelligence across diverse domains.
At the heart of this survey lies an elegant framework that breaks down LLM-based agents into three essential components. Much like how a telescope requires a lens to gather light, a mount to position and stabilize it, and controls to direct its focus towards celestial objects. The framework consists of the brain, which handles reasoning and decision-making, the perception component that allows the agent to sense and interpret its environment, and the action module that enables the agent to take meaningful steps in the world, with each component working in harmony to create truly functional artificial beings. The researchers then dive deep into the practical applications of these LLM-based agents, examining how they perform across three distinct scenarios that showcase their remarkable versatility and potential. Like a theater company that can stage intimate solo performances, dynamic ensemble pieces, and interactive shows where audience members join the cast, these agents excel in single-agent scenarios where they work independently, multi-agent environments where multiple AI systems collaborate or compete, and human-agent cooperation settings where artificial and human intelligence blend seamlessly together. Perhaps most intriguingly, the survey explores the emergence of agent societies, where collections of LLM-based agents begin to exhibit complex behaviors, personalities, and social phenomena that mirror and sometimes illuminate aspects of human civilization. Imagine an ant colony where each individual ant possessed human-like reasoning abilities, forming intricate social structures, developing unique personalities, and creating emergent behaviors that offer profound insights into how our own societies function, evolve, and sometimes stumble in their quest for collective intelligence and cooperation. The significance of this work extends far beyond academic curiosity, representing a comprehensive roadmap for researchers and practitioners who are building the next generation of intelligent systems that could fundamentally transform how we interact with technology. Like a detailed atlas created by early explorers for those who would follow, this survey provides essential guidance for navigating the complex landscape of LLM-based agent development, highlighting both the tremendous opportunities and the challenging territories that still require careful exploration and understanding. What makes this survey particularly valuable is its recognition that the field has moved beyond incremental improvements in narrow AI systems towards something far more ambitious and transformative. The authors acknowledge that while previous efforts focused on enhancing specific capabilities or optimizing performance on particular tasks, like a mechanic fine-tuning individual engine components, the real breakthrough lies in having a general, powerful foundation that can be adapted and specialized for countless different applications and environments. The paper also addresses the crucial open problems and key topics that researchers must tackle as this field continues to evolve, from technical challenges around reliability and control to broader questions about safety and societal impact. Think of it as a lighthouse keeper's detailed log, not only documenting current conditions and successful navigation routes, but also warning of hidden rocks, unpredictable currents, and weather patterns that future voyagers will need to understand and prepare for as they venture into these largely uncharted waters. By providing this comprehensive survey, the authors have created an invaluable resource that synthesizes years of research, identifies patterns and trends, and establishes a common vocabulary for discussing these sophisticated AI agents. Like a master librarian who has carefully cataloged, cross-referenced, and annotated thousands of manuscripts to create a single, accessible guide to human knowledge, this work brings together disparate research efforts into a coherent framework that both newcomers and experts can use to advance their understanding and contributions to the field. As we drift towards sleep,
we can appreciate how this survey represents a pivotal moment in artificial intelligence research, where the dream of creating truly intelligent agents is closer to reality than ever before, thanks to the foundational capabilities of large language models and the growing understanding of how to harness their potential. The work stands as both a celebration of how far we've come and a roadmap for the extraordinary journey ahead, where AI agents may soon work alongside us as partners, collaborators, and perhaps even friends in our ongoing quest to understand intelligence itself, whether artificial or human. Allow yourself to feel wonder at this transformation, how language models grew from narrow tools into versatile foundations for AI agents that can tackle diverse challenges. It's like watching raw potential become refined capability. Breathe gently and let these concepts flow through you without strain. Next, we'll explore a breakthrough called GPT-3, where researchers discovered that dramatically scaling up AI could fundamentally change how these systems learn. We'll see how bigger models began learning from just a few examples, much like humans do.
Imagine a student who has spent years reading every book in a vast library, absorbing patterns of language and meaning from countless texts, and now sits ready to tackle any new challenge you might present. This paper introduces GPT-3, a language model with 175 billion parameters that represents a dramatic scaling up of artificial intelligence capabilities, trained on enormous amounts of text to understand and generate human language with unprecedented sophistication. The researchers wanted to explore whether simply making language models much larger could fundamentally change how they learn new tasks, moving away from the traditional approach of fine-tuning models on thousands of task-specific examples towards something more resembling human-like learning from just a few demonstrations. Think of a master chef who can taste a new dish and immediately understand how to recreate it, needing only a few bites rather than weeks of practice in culinary school. The key insight driving this research is that while current natural language processing systems typically require extensive task-specific training with thousands or tens of thousands of examples, humans can often learn to perform new language tasks from just a few examples or simple instructions, a capability that has remained largely elusive for AI systems. The researchers hypothesized that by dramatically increasing the scale of language models, they might unlock this more flexible, few-shot learning ability that mirrors human linguistic adaptability. Picture a massive telescope that can see distant galaxies invisible to smaller instruments, where raw size enables entirely new types of observation and discovery. GPT-3 represents exactly this kind of scaling breakthrough, containing 175 billion parameters, which is 10 times larger than any previous non-sparse language model, a quantum leap in computational scope that the researchers believed might reveal emergent capabilities not visible in smaller models. Rather than following the conventional approach of pre-training followed by fine-tuning on specific datasets, the team chose to test GPT-3's performance using only few-shot learning, where the model receives tasks and demonstrations purely through text interaction without any gradient updates or traditional training adjustments. Consider a versatile musician who can pick up an unfamiliar instrument and, after hearing just a few notes of a song, begin playing along in the same style and key. The researchers put GPT-3 through an extensive battery of tests across diverse natural language processing tasks, including translation between languages, question answering systems, and close tasks, where the model fills in missing words, all without any task-specific fine-tuning or adjustment of the model's internal parameters. What made these experiments particularly remarkable was that GPT-3 achieved strong performance on many of these datasets, sometimes even reaching competitiveness with prior state-of-the-art approaches that had been specifically fine-tuned for each individual task. Think of a gymnast attempting increasingly complex routines, succeeding at some spectacular moves, while stumbling on others that require different types of coordination and balance.
Beyond standard language tasks, GPT-3 demonstrated impressive capabilities on challenges requiring on-the-fly reasoning and domain adaptation, such as unscrambling jumbled words, using novel words correctly in sentences, and even performing arithmetic with 3-digit numbers, all tasks that demand flexible thinking rather than mere pattern matching. However, the researchers also identified several datasets where GPT-3's few-shot learning approach still struggled, revealing the boundaries and limitations of this scaling approach, along with some methodological challenges related to training on large web corpora that could introduce biases or inconsistencies.
Imagine a skilled forger whose paintings become so convincing that art experts struggle to distinguish them from authentic masterpieces, creating both wonder and concern in the art world. One of the most striking findings emerged when the researchers tested GPT-3's ability to generate samples of news articles, discovering that human evaluators had significant difficulty distinguishing these AI-generated articles from those written by human journalists, a result that highlights both the remarkable sophistication of the model's language generation capabilities and raises important questions about the broader implications of such technology. This finding prompted the research team to engage in thoughtful discussion about the societal impacts of GPT-3, recognizing that tools capable of generating human-like text at scale carry both tremendous potential benefits and significant risks that merit careful consideration. Picture a turning point in a river where the water changes direction entirely, marking a fundamental shift in the landscape that everything downstream will be shaped by. This research represents a pivotal moment in artificial intelligence and natural language processing, demonstrating that scaling up language models can unlock qualitatively different capabilities, moving beyond incremental improvements toward a new paradigm of few-shot learning that more closely resembles human linguistic flexibility. The implications extend far beyond academic benchmarks, suggesting that sufficiently large language models might serve as general-purpose tools capable of adapting to diverse tasks without extensive retraining, fundamentally changing how we think about building and deploying AI systems. Think of a master key that can open many different locks, each requiring a slightly different approach, but all yielding to the same fundamental tool when wielded with skill. The significance of this work lies not just in GPT-3's impressive performance across diverse tasks, but in the broader principle it demonstrates about the relationship between scale and capability in artificial intelligence, suggesting that some problems in machine learning might be solved not through more sophisticated architectures or training techniques, but through the relatively straightforward approach of building larger models with more parameters. This finding has profound implications for the future direction of AI research, indicating that the path toward more human-like artificial intelligence might run through continued scaling, rather than fundamentally new algorithmic approaches. Take time to appreciate this shift. AI systems learning to understand new tasks from just a few examples, approaching something closer to human-like learning. It's quite different from the old way of training systems on thousands of specific examples, isn't it? Let this realization settle comfortably within you. Now we'll discover how researchers began combining these large language models with autonomous agents, creating systems that can walk, talk, and make decisions independently. We'll explore this fascinating merger of knowledge and action. Picture a library where every book has suddenly learned to walk, talk, and make decisions on its own. And you'll begin to understand the fascinating world that researchers are exploring when they combine large language models with autonomous agents. For decades, scientists have been working to create artificial agents that can act independently, make decisions, and solve problems without constant human guidance. But these efforts have typically involved training systems within very narrow, isolated environments with limited knowledge bases. This approach has created agents that, while capable in their specific domains, operate in ways that feel quite foreign to how humans actually learn and think.
making it difficult for them to achieve the kind of nuanced, contextual decision-making that we take for granted in human intelligence. The landscape of artificial intelligence shifted dramatically when large language models began absorbing vast quantities of knowledge from across the web, demonstrating capabilities that approach human-level intelligence in many domains. Like a master craftsman who has spent years accumulating skills and knowledge from countless projects, these language models have developed a remarkably broad understanding of the world through their exposure to diverse text and information. This breakthrough has opened up entirely new possibilities for creating autonomous agents, sparking a surge of research into how these knowledge-rich models can be transformed into independent actors capable of reasoning, planning, and executing complex tasks in ways that mirror human cognitive processes. The researchers behind this comprehensive survey recognized that this rapidly evolving field needed a systematic examination, much like cartographers mapping a newly discovered continent with all its varied territories and hidden connections. Their work represents the first holistic attempt to understand and organize the diverse landscape of research into LLM-based autonomous agents, bringing together scattered studies and emerging trends into a coherent framework that can guide both current practitioners and future researchers. By taking this bird's-eye view approach, they've created an essential resource for anyone trying to navigate the complex and quickly expanding world of intelligent autonomous systems.
The survey begins by examining how these LLM-based autonomous agents are actually constructed, proposing a unified framework that acts like a master blueprint capable of describing the architecture of most existing systems in the field. This framework provides researchers with a common language and structure for understanding how different teams approach the challenge of combining large language models with autonomous decision-making capabilities, revealing both the shared principles and the creative variations that emerge when brilliant minds tackle similar problems from different angles. Through this systematic approach to categorizing construction methods, the authors help bring order to what might otherwise appear to be a chaotic collection of experimental approaches and novel techniques. Moving beyond the technical foundations, the survey explores the remarkable diversity of real-world applications where these intelligent agents are making their mark, spanning 3 major domains that encompass much of human knowledge and activity. Like seeds carried by the wind to take root in vastly different soils, LLM-based autonomous agents have found fertile ground in social science applications, where they can simulate human behavior and social interactions, in natural science contexts where they assist with research and discovery, and in engineering domains where they tackle complex design and optimization challenges. This broad applicability demonstrates the versatility and power of combining language understanding with autonomous decision-making capabilities. Understanding how to properly evaluate these sophisticated systems presents its own complex challenges, which the survey addresses by examining the various strategies researchers have developed to measure agent performance and capabilities. Think of evaluation like designing a comprehensive fitness test for athletes who compete in entirely different sports, each requiring different skills, strengths, and measures of success. The authors explore how researchers assess everything from basic task completion and accuracy to more nuanced qualities like adaptability, reasoning ability, and the capacity to handle unexpected situations, revealing both the progress made in evaluation methodologies and the ongoing challenges in creating fair and comprehensive assessment frameworks. The survey doesn't simply catalog existing work, but also thoughtfully identifies the significant challenges that researchers continue to face, along with promising directions for future exploration and development. Like experienced mountain guides pointing out both the treacherous paths to avoid and the promising routes that might lead to new peaks, the authors highlight fundamental issues such as ensuring reliable performance, managing computational costs, addressing safety concerns, and improving the alignment between agent behavior and human values. Their analysis provides a roadmap
for researchers looking to contribute meaningfully to this field, while also helping readers understand why certain problems remain difficult and what breakthroughs might be needed to overcome them. Perhaps most importantly, the researchers have committed to keeping their survey current and relevant by maintaining an actively updated repository of references and new developments. Recognizing that this field evolves at a pace that quickly makes static publications obsolete. This living document approach, like tending a garden that requires constant care and attention to flourish, ensures that their comprehensive overview remains a valuable resource as new papers emerge, novel techniques are developed, and the boundaries of what's possible with LLM-based autonomous agents continue to expand. Through this ongoing commitment, they've created not just a snapshot of the current state of research, but a continuously evolving guide that will serve the research community for years to come. Rest with that image of knowledge becoming active and autonomous, libraries of information that can now act and decide for themselves. It's both fascinating and represents such a fundamental shift from passive information to active intelligence. You can simply let the wonder of this development wash over you. Finally, we'll see how researchers solved a key limitation by teaching AI systems when and how to use external tools. We'll discover how language models learn to reach beyond their own capabilities when needed. Picture a brilliant student who excels at creative writing and complex reasoning, yet struggles with basic multiplication tables, so they learn to reach for a calculator when needed. This captures the essence of what researchers have accomplished with Toolformer, a language model that has taught itself to use external tools. Large language models have shown us remarkable capabilities, solving new tasks. From just a few examples are simple textual instructions, especially as they grow in scale. Yet they paradoxically stumble on basic functionality, like arithmetic or factual lookups, tasks where much simpler and smaller models excel effortlessly. The researchers behind this work recognized this fundamental limitation and developed a solution that allows language models to bridge this gap, teaching themselves to use external tools through simple APIs to achieve, as they put it, the best of both worlds. Think of a master chef who has learned not just recipes, but when to use each kitchen appliance, how long to set the timer, and which ingredients to add at precisely the right moment. Toolformer operates with similar intuitive decision-making about tool usage. The model has been trained to make sophisticated judgments about which APIs to call, determining the optimal timing for each tool invocation, deciding what specific arguments to pass to each external system, and perhaps most impressively, learning how to best incorporate the results back into its future token predictions. This represents a significant leap beyond simply having access to tools, moving into the realm of strategic tool deployment where the model understands not just the what, but the when and how of external resource utilization. Like an apprentice watching a few demonstrations before mastering a craft independently, Toolformer achieves this sophisticated tool usage through a self-supervised approach that requires nothing more than a handful of demonstrations for each API. This elegant training methodology sidesteps the need for extensive human annotation or complex reward systems, instead allowing the model to learn from minimal examples while developing its own understanding of when and how to leverage external capabilities. The self-supervised nature of this approach makes it particularly attractive for practical deployment, as it dramatically reduces the overhead typically associated with training models to use new tools or APIs. Imagine a Swiss Army knife with each blade perfectly suited for different tasks. Toolformer incorporates a diverse range of tools, including a calculator for mathematical operations, a question and answer system for factual queries, 2 different search engines for information retrieval, a translation system for language conversion, and a calendar for temporal reasoning. This variety demonstrates the generalizability of the approach, showing that the underlying methodology isn't limited to a specific type of tool or domain, but can be applied across the spectrum of functionality that language models typically struggle with. Each tool addresses a different weakness in traditional language model capabilities, creating a comprehensive system that maintains the strengths of large language models while shoring up their notable deficiencies. Consider a small, efficient car that suddenly gains the performance of a much larger vehicle through strategic upgrades. Toolformer achieves substantially improved zero-shot performance across a variety of downstream tasks, often competitive with much larger models, without sacrificing its core language modeling abilities. This performance improvement represents more than just incremental gains. It fundamentally changes the value proposition of language models by eliminating the need to scale up model size to achieve better performance on tasks that require external knowledge or computational capabilities. The fact that these improvements come without degrading the model's original strengths suggests that tool usage integration can be achieved without the typical trade-offs that plague model modifications.
Like a telescope that brings distant stars into clear focus, this research illuminates a path forward for making language models more practically useful while maintaining their creative and reasoning capabilities. The zero-shot performance improvements across diverse downstream tasks suggest that Toolformer's approach could be broadly applicable, potentially transforming how we think about the capabilities and limitations of language models in real-world applications. Rather than accepting that language models must choose between being large and capable or small and efficient, this work demonstrates that strategic tool integration can provide a third path, one where models can remain computationally reasonable while gaining access to the precise, factual capabilities they've traditionally lacked. Think of a master conductor who knows exactly when each section of the orchestra should contribute to create a harmonious symphony. The implications of this research extend far beyond the specific tools demonstrated, suggesting a new paradigm for AI system design. By teaching language models to recognize their own limitations and strategically delegate to specialized systems, we move toward a more modular, efficient approach to artificial intelligence that leverages the strengths of different computational approaches, rather than trying to force a single model to excel at everything. This self-aware tool usage represents a form of meta-learning that could fundamentally change how we build and deploy AI systems, moving away from monolithic models toward more collaborative, tool-augmented architectures. As we settle into sleep, let this research remind us that sometimes the most elegant solutions come not from building bigger hammers, but from teaching our tools to recognize when they need help and knowing exactly where to find it. Creating systems that are both humble enough to acknowledge their limitations and sophisticated enough to transcend them through strategic collaboration. As we reach the end of our gentle journey tonight, let yourself rest with the full picture of what we've witnessed together. We've seen how programming evolved from manual, painstaking work to sophisticated AI agents that can write, test, and improve code autonomously. We've discovered that the most remarkable part isn't the technology itself, but how programmers have embraced these AI companions that are transforming their entire profession. The future of software development is being written by artificial intelligence, and rather than resist this change, the programming community has welcomed it with open arms. Let these insights settle softly as you drift toward peaceful sleep, knowing that remarkable transformations often happen not through conflict, but through collaboration and acceptance.